a single laser pulse can vaporize a tiny amount of metal off a piece of orbital debris. That vaporization acts like a tiny rocket. Push enough of those rockets and the junk falls back to Earth. NASA published this idea in 1996, Project ORION, lead author, Claude Phipps. The physics is straightforward. A focused laser hits metal, the surface vaporizes into plasma. The plasma escapes at high velocity. By Newton's third law, the debris is pushed in the opposite direction. The debris piece is orbiting at 27,000 kilometers per hour at an altitude of 660 kilometers. Each pulse nudges it, microscopically, but over weeks of repeated pulses, it falls. Eventually, the atmosphere catches it, and it burns up, cleanly, without creating more debris. One ground station, in principle, could clean the most crowded altitudes of low Earth orbit. Per piece, it would cost a fraction of what physical capture missions cost today. Meanwhile, ClearSpace's first capture mission, reportedly around 86 million euros to remove one piece of debris. A laser ablation system, over its lifetime, could potentially deorbit many pieces for a fraction of the cost. The technology has existed on paper for 30 years. So why is no ground station firing right now? 3 reasons. Each one is harder than it sounds. Reason 1. The engineering is brutal. You're hitting a 10-centimeter object moving at 27,000 kilometers per hour, 660 kilometers away, through 660 kilometers of atmosphere that distorts your beam every microsecond. You need adaptive optics, thousands of micro mirrors flexing 1,000 times per second. Reason 2. The power. Commercial industrial lasers max out at 100 kilowatts. You need megawatts. Megawatts of laser output means megawatts of waste heat. The cooling alone is the size of a building. Reason 3. The cost. Ground-based systems can run into the hundreds of millions of dollars, space-based into the billions. And every proposal, Project ORION, NASA's CLIMS, the Russian so-called Echelon program, has stalled at funding, even with the engineering, even with the money. There is a 4th reason, the biggest one. The same laser that clears space junk can also disable a working satellite. Photons carry momentum, tiny but measurable. Concentrated, they can vaporize metal at the surface. The metal becomes plasma. The plasma erupts outward, carrying momentum away from the surface. And by conservation of momentum, the debris piece gets pushed in the opposite direction. Each pulse vaporizes roughly 10 micrograms, about 1/10 the mass of a grain of salt. But pulse it 10 times per second, or 100, and the cumulative effect compounds. Now, the engineering problem. The atmosphere is in the way. It distorts your focus. The solution? Adaptive optics. A mirror with thousands of independent microsegments. Each segment flexes many times per second, correcting atmospheric distortion in real time. We already have this technology. It's how the world's biggest telescopes see clearly through the atmosphere. Used in reverse, it can also pre-distort a laser beam so it arrives at orbit cleanly focused. Then, the next problem, hitting a moving target. A 10-centimeter object at 27,000 kilometers per hour moves its own length every 13 microseconds. Your laser tracking system has to predict the debris position with millimeter precision. Computers can do this. The math is hard but solved. And the energy budget. Estimates suggest the energy required to reliably deorbit one piece could be substantial, varying widely depending on object size and orbital parameters. 3 megajoules is roughly the energy in about 1/10 of a liter of gasoline per piece of debris removed. Compare that to launching a rocket to physically grab the same piece, hundreds of gigajoules. The laser is estimated to be orders of magnitude more energy efficient per piece removed. The physics works, the math works, the energy economics work brilliantly. And yet, as of now, no fully operational debris ablation system exists. anywhere on Earth. Why? Because the engineering problem isn't the real problem. The real problem is in conference rooms, not in observatories. It's in the answer to one question. Who do we trust with a megawatt laser pointed at orbit? Mount Stromlo, Australia, 40 kilometers from Canberra. EOS Space Systems. This is among the closest any commercial company has reportedly come to developing a debris removal laser system. EOS already tracks thousands of objects in orbit with laser precision telemetry. The same hardware that tracks could, with one engineering decision, also ablate. EOS has not made that decision. Not yet. Russia tried. The so-called Echelon program reportedly began in 1981, paused indefinitely after the Soviet collapse. China publishes laser ablation papers regularly. Theoretical, always theoretical. NASA's CLIMS proposal, conceived around 2011, reportedly never funded. The cooling alone for a megawatt laser running continuously requires building-scale infrastructure. Pulsed lasers store and dump energy at megawatt scale. The capacitor banks alone can fill entire rooms or buildings. Then there's geometry. The Earth rotates. The debris orbits. Your window to hit any specific piece is seconds. Repeated every 90 minutes when the same piece comes around again. Hundreds of pieces in your firing queue. Each one needs precise scheduling. Ground-based installation cost estimates from various studies vary widely, ranging roughly from hundreds of millions to billions of US dollars. Space-based systems, potentially billions of dollars at minimum. And they need servicing missions. Every proposal has died at funding, including the cheap proposals, even the bargain proposals. And most governments that could fund one have chosen not to. Why? Because the very act of firing a laser at orbit is politically classified as ambiguous. A laser firing at debris is, in nearly every measurable way, indistinguishable from a laser firing at a working satellite. The only difference is what's in the targeting log. And targeting logs can be edited. So when any nation announces a ground-based laser facility for debris removal, every other spacefaring nation has to decide, are they really cleaning or are they building a weapon? The Outer Space Treaty of 1967 bans weapons of mass destruction in space, but doesn't ban anti-satellite weapons specifically. It creates norms, not hard prohibitions. Norms can be broken, and nations know exactly what happens when they are. January 11th, 2007. The FY-1C Chinese weather satellite, destroyed, and its debris tracked. China launched a ground-based interceptor, destroyed it, created thousands of trackable debris fragments. Most of those fragments are still up there. They will be for centuries. February 20th, 2008, USA 193, an American spy satellite in failed orbit. The US destroyed it with a Navy missile, officially to protect against toxic fuel. March 27th, 2019, India Mission Shakti, a target satellite at 280 kilometers altitude. India became the fourth nation to successfully destroy a satellite in orbit using a ground-based missile. November 15th, 2021, Russia, Cosmos 1408, defunct Soviet-era satellite. Russia launched a Noodle direct ascent missile, destroyed it, created over 1,500 trackable fragments. The ISS crew sheltered in their return capsules within hours. 4 nations, 4 events, 4 debris clouds that will outlive every government that authorized them. Every nation that wants a debris removal laser is suspected of wanting an ASAT weapon. Because there is no observable difference between the two systems before the laser fires. And after it fires, the targeting log is the only evidence of intent. Targeting logs are classified by the nation that owns the laser. which means trust requires inspection, which no nation will permit, which means trust is impossible. This is why China and Russia would be terrified of an American debris laser, and why the US would be terrified of a Chinese or Russian one, and why a European laser would scare both, and an Indian laser would scare everyone. Every nation that could build one fears every other nation more than they fear orbital debris. And so, the cheapest debris solution, the most efficient one, the one researchers have been discussing since the mid-1990s, remains unbuilt by collective decision of every nation that could build it. Meanwhile, the debris field grows. And the math from Friday's short still holds: a handful of cleanup missions versus thousands of dangerous objects. Back to Mount Stromlo. EOS Space Systems. Australia. EOS doesn't have nuclear weapons. EOS doesn't have a permanent UN Security Council seat. EOS is Australian, civilian, commercial, trusted, in a way that no major power laser ever could be. If anyone is going to break the impasse, it might be a country small enough that nobody fears them. EOS has not announced ablation capability, not yet. The hardware is ready. The political authorization is what's missing. Australia is a small country with a large alliance, Five Eyes membership, American technology partnerships, trusted by the West, but also not threatening. Australia doesn't have geopolitical incentives to misuse a debris laser. If EOS announces ablation, it changes the entire field. Suddenly, a debris removal laser becomes operationally possible, not just theoretical. Other nations would have to respond. They'd either match it or accept it. Match it, a global race to ground-based laser ablation capability, trust through transparency. Or accept it, a quiet, diplomatic precedent that civilian commercial actors can do this work. Either way, orbit gets cleaner, faster, at a fraction of the cost. The math from Friday's short still says just a handful of active cleanup missions versus thousands of dangerous objects. Mechanical capture can't scale. Lasers might be the only thing that can. The choice we face: build the lasers and learn to trust each other, or watch Kessler syndrome play out in real time. Kessler syndrome doesn't take centuries to play out. It might take decades. Once it starts, the cascading collisions remove low Earth orbit from human use for generations. No GPS, no weather satellites, no global internet, no new launches. For our children's children, we can't afford to wait for diplomats to agree. We can't afford to act before they do. We need a path neither side has tried yet. A small civilian actor doing the right work, transparently. If EOS, or some company like them, pulls the trigger, the orbital economy gets a chance. The next chapter is about who pays, who decides, and whether the orbital economy can do what the orbital engineering can't.